All right. So exam 5, if you can't tell, is going to be all about power stuff. All right. So basically beginning with the homework we had last week and continuing with the stuff that we have this week, which gets us into a concept called three-phase power, which I'm going to introduce a little bit today. We're not going to cover that in too much detail, but just enough to make you guys familiar with the idea. Okay. So one of the things we introduced last week, we talked about the idea of, at the very, very end of class on Friday, this idea of power factor correction. So I'm going to maybe address a question that came up today as I was coming in the room here. These guys were asking me a question here in the room about what is reactive power. Apparently they said they can see real power. I don't know how they can see that, but I get the idea. Right? It's a little bit more intuitive what that means. Okay. So let's say we're going to deal with an example today. So specifically, the example I'm going to deal with gets into a load here that's going to be 10 kilowatts and 8 kilobars. All right. If I wanted to find the power factor, how would I find the power factor for that? So 10 kilowatts and 8 kilobars. How would I find the power factor of that?
Find the magnitude.
Yeah, find the magnitude of that. And then what do I know? I know that P is equal to the magnitude of S times cosine of the angle. And this guy here is the power factor. Okay. That would be my approach for trying to figure that out if I wanted to. I think in this case, I don't know what this guy's going to be, somewhere around 0.8 something. All right. I'm not going to calculate it right here, but it's probably around 0.8 something. Okay. Back to my original point though, this load that I've got right here, let's just take for a moment. Let's just say I don't want to deal with this system right here where I've got a voltage source and I'm throwing in what I call a transmission line. So I've got there's some wire that exists between the power station and the load, right? There has to be, because power has to be directed from the source to the load. So let's just assume that guy was ideal for a minute, right? So I had a voltage source here, V sub S, and I have a load. Okay. Let's just say, for sake of argument, that this load was just a pure inductor. Okay. All right. And if that load was a pure inductor, the question I'm asking about this is, how much P and how much Q would this guy get? How much P would that load get right there?
0 P.
Zero P, right? There would be no real power going to that load, but there would be a reactive power going to that load, right? So what does that mean? What does that mean to say? So this is the question, right? So this guy has no real power. So what does it mean to say that no real power is going to that thing?
No power is being absorbed.
No absorbed energy.
No absorbed energy, right? There is essentially what's going on with, if P is 0, that means there is no energy being absorbed into that thing. The power P of T is basically half the time above 0 and half the time below 0, meaning you're storing energy in it half the time, and then you're spitting that energy back onto the grid. So it takes energy from the grid, then puts it back on the grid, takes it, spits it back, okay? So it spends half the time doing that. The problem from the utilities perspective, right? So this is what it means. When I have a reactive power, what it means is that there's some amount of current that's flowing in this system. So some amount of the current I of T here that is flowing in this system, basically to transfer energy into that inductor and then out of the inductor. From the utilities perspective, that's a bad use of current, right? Because that current gives us losses in this transmission line here. So in my example here, where I've got a transmission line that has 0.05 ohms of resistance, there is going to be some loss in that resistance as a result of that current that is going to that reactive load. All right, now, natural question might be, well, but the load is reactive, so it needs that current, and it does, right? But what we're going to see here today is what I can do is I can maybe put a source of Q, capacitor source Q, right? So I can take a source of Q and put it in parallel with that inductor and effectively almost get rid of that Q, all right? Which gets rid of the corresponding current, right? That's the basic idea, all right? So Q is problematic from the utility's perspective because you could source it yourself. The utility doesn't need to necessarily source you the Q. You can source a lot of the Q on your own. All right, you guys follow that? Questions about that? About what is Q?
What is the load doing?
What is the load doing?
Yeah, so like we're putting Q into that, which is dropping the current.
So if my load is a pure Q, what that probably means is I'm somehow creating a magnetic field in that load, right? So I have, if what I have is just a giant inductor, let's say my load is a giant inductor, then what I'm doing is I'm creating a giant magnetic field with that thing, right? And so what's going on is I'm having to pull current from the grid to establish that magnetic field. I'm storing energy in it, but to say that I'm storing energy in it just basically means that I'm absorbing energy in and then I'm giving that energy back out. There's no net conversion of energy into real work, right? The idea here is if I'm just storing energy, then what I can do is I can store it, absorb it, so I can absorb it, spit it back out, absorb it, spit it back out. That magnetic field stays established that whole time.
So is it fair to say then that Q represents a magnetic?
Q represents current that has to flow in the grid to establish energy storage, right? To keep the magnetic field in that inductor, right? There is Q that has to move back and forth. There's current that has to move back and forth between the grid and that inductor to keep that magnetic field going. But that magnetic field is stored energy. It does not represent energy that is being converted to some other form. If I have average power, there is energy being converted to some other form, like in a resistor, right? If I have 100 watts in a resistor, then I'm converting 100 watts of electrical energy into 100 watts of heat or light or something like that, right? Or in the case of your cell phone, if I have a 25 watt charger for a cell phone, then 25 watts of electrical power goes in, and then what comes out of that is some amount of heat and some amount of stored energy in the battery. Tyler, you look like I just baked your brain.
It's hard to think about, kind of like trying to imagine something in a couple different planes at once.
Well, P represents, this is, I mean, it's not a critical point, but P, it is important. P represents real work, real energy conversion, right? If there is 100 watts of P, then there is real energy conversion that's happening. Electrical power is becoming something else. If there is 100 VARs of Q, that represents current that has to flow to maintain energy storage. Okay. And there's no real energy conversion that's coming from that. It's sort of imaginary, yeah. It's not really imaginary, but it's a real current that flows. It's a way of us thinking about the current that flows, because that Q.
So Q is a current then?
Q causes a current, yeah. So if I have a load that has no average power, there is a current that goes into that, right? If I had a voltage source and an inductor, right? If I have a voltage source in series with an inductor, there's a current that flows into that inductor. But that current doesn't represent anything that becomes real work. Okay. All right. So the idea, though, is if I'm the utility, I would like to minimize that amount of current that flows, right? And only really try to give you current that relates to your actual energy conversion need. All right, the kind of thing that I need to convert. If I need to get power out of, let's say, gas or photons from the sun or whatever, my primary concern is that this voltage source provides me the energy that gets into real work on the other side. Okay. All right. So this, so you can go back and look at this later, but basically what we just talked about, right? Q sub L is the reactive power that creates the magnetic fields and electric fields, right? It's that energy storage that's required to make physical processes happen. P is the real power, which represents the time average conversion of electrical energy into something else. All right, so I want to get to an example here. So let's say I've got this. So, well, what I started with, this guy's got 10 kilowatts and 8 kilobars. All right, and he's got 250 volts with 0 angle across him. All right, according to this picture. Right. So let's say here that I want to figure out what the magnitude of the current is. So I want to know, what is the current I sub S that's flowing right here. And this is one of those situations, I'll draw a voltage source in so you guys feel better about that. Okay. All right. So in this particular case, if I want to figure out the magnitude of S, how would I figure out the magnitude of SL here? What would be the way to, and first of all, magnitude of SL, what is the name of that?
Apparent power.
This guy is the apparent power, yes. All right. Apparent power is the magnitude of the complex power. If I just have S, that's the complex power. Okay. All right, so the magnitude of that, in this case, is easy to get, right? There's no weird trig. I just have 10,000 squared plus 8,000 squared. And I take the square root of that. So if I go through that math, I think I get 12.806. What are the units I should use here for apparent power?
Volt amps.
Volts amps. I do kVA. Okay. All right. Now, if I want to figure out the current, the simplest thing for me to do is to just work with my magnitudes here, right? So, right, this guy is equal to V times I conjugate. So if I take the magnitude, right, SL equals V times IS conjugate, right? If I take the magnitude of both sides here, that just becomes the magnitude of S equals the magnitude of V times the magnitude of I, right? So if the magnitude of I becomes 51.225 amps, okay? And this is an RMS value here because this was RMS. So let's see if we can ground ourselves. If I say that that current is 51.225 amps RMS, if I looked at the actual current, or in other words, if I looked at the real current as a function of time, what would that look like?
Positive.
So if I have a 51.225 amp RMS current, what does that mean the current looks like?
It's constant.
Nope. Well, it's constant something, constant amplitude, right?
Yeah.
What's it look like? It's gonna, well, I don't know what the phase angle is, right? But it's gonna be sinusoidal, cosinusoidal, right? And what's the peak value of this thing gonna be?
Should be 72, right? Because you would multiply the RMS.
Yes, I do 51.225, times the square root of 2 would be the peak value of that thing, right? That would be its peak value. All right. Again, we use the RMS number as really sort of the amplitude now, right? And the reason we do that, we get those over 2 values out of our power relationships. And most of the time, I didn't do it at the very beginning because I didn't want to cause you further confusion when we first started doing AC circuits. But most of the time, when we talk about phasors, most of the time people do use RMS values instead of peak values. All right, it always seems to me like an additional layer of confusion to add to you guys back in February. All right. Maybe I should have added it then, but it seems like you guys I think people deal with it better when it gets introduced in the context of where it needs to be introduced, right? All right, so I get that. Now the question basically is, so if I have this load right here, so this load is 10 kilowatts plus J times 8 kilovars. What type of load is this? Is this a leading or lagging load?
So
Let me ask it this way. Is it inductive or capacitive?
it's inductive
It's inductive. Why is it inductive?
because the phase is positive.
The phase of this is positive. Yeah, because the complex power has an angle that is the same as the angle of the impedance. And the impedance angle is positive. I keep wanting to write theta. The impedance angle is positive when I have an inductive load. So this is an inductive load, okay? All right, so if I have an inductive load, I can always go back to that table that I gave you guys. But if I have an inductive load, what does this mean? Leading or lagging?
Lagging.
Lagging, okay? So this guy is lagging, which means that I lags V, okay? All right, I lags V. So in this particular case, then I know that the current has to be a little bit behind the voltage angle, right? And I could figure out if I wanted to. I got all the information I need to figure that out, right? I'm not too concerned about that though right now. We can look at that if people really want to, but that's all I need to know for the moment, okay? So if I were to draw what this S sub L looks like, let me think of it this way, right? Here's P, here's S sub L as a vector. So the length of that side, I guess, is the magnitude. This guy would be my Q, okay, like that. And I call it PL and QL, like that. All right, and this angle would be phi Z, the angle of the impedance, okay? What could I potentially do? Let's say I didn't want to supply that Q from the source, right? Right now, that Q is coming from the source. What if I didn't want to do that? What would happen if I did this? Let's say I put a capacitor in parallel with this guy. What do we know about the Q of a capacitor?
It's stored.
It's negative. Negative, right? This guy has a negative Q. In other words, he's going to push current. His current has a different phase than the current of the inductor. So what that's saying is this guy is basically a negative Q, right? So I can basically choose a capacitor here that has a negative Q, whereas the inductor has a positive Q. And if I did that, if I added to this load a negative Q, right, I could have some load that has, so Q, so this is my load, not load, okay? This is my load. I could add to that some load that has a pure negative Q. Call it Q capacitor, okay? If I added that in parallel with that load, if I had the right value capacitor that had the right value of Q, then I could make the total Q of that load. So the load in this case now would be, I'll draw a box around it, right? Draw a box around this whole thing here, right? So I have a capacitor in parallel with that load. I can make the total Q of that thing 0.
And that's the goal.
That's the goal, right? If I do that, what that's going to do is it's going to reduce the need for L1 here to draw his Q from the grid. What should that do to the current that I'm drawing from the grid?
Help with the losses, right?
It's going to reduce the magnitude of that current, which is going to help the losses. All right, you guys follow that?
So the capacitor is, so there's still some current flowing, but there's a lot less current flowing with the capacitor here.
Yeah, that's right. So basically what I'm doing is I'm putting this capacitor here to deal with providing, so if SL here has 8 kVARs that it requires supplied to it, I could potentially choose this guy to supply at least some portion of that 8 kilobars. All right, so this guy has a negative Q. That's the important thing about this guy. The capacitor has, J times QC, where QC is a negative value. So the total power delivered to the load is basically whatever's going to this guy plus whatever's going to this guy, right? So what I've written here, the total power is equal to SL, right? The load power plus J times QC. So if I look at the math here, right? Basically what I'm saying is I'm adding their reactive powers. And I'm trying to supply some amount of the Q from the capacitor and some of the amount of the Q, all right, potentially from the grid. Okay. Now, so essentially all I'm doing is saying I just got to put a capacitor in parallel with that, and I got to figure out, well, how do I size that capacitor? So how should I approach that problem, do you think?
And wouldn't you want to use the power factor, since that's the kind of the ratio of it?
Yeah, so I would. So let's take this example right here. Let's say what I want is I want to choose this capacitor. So this is my total now for that load, right? So it's going to be the load's power. Okay, so let's see it. This is the load power, and this is the capacitor. And what I want to do is I want to make it such that I completely cancel the power, the reactive power that the load is trying to take on. Okay, so the reactive power, so this Q sub L here, this guy is 8 kilovars. Okay, so what I'm saying is my goal in this particular case is to have the load just simply absorb a real power. Okay, so I could think of this guy as this, PL plus J0. So in the context of like problem, I don't know if it's problem 2 or problem 3 on the homework, I call this guy here Q target. And my Q target is basically QL minus QC. And if I want that to be 0, then I have to make sure that my capacitor can supply how much Q?
Much Q is L.
Yeah, it needs to supply as much Q as the L is requiring. So in this particular case, QL is 8 kilovars. Okay, QL is 8 kilovars. How much does QC have to be?
8
Yep.
kilobars.
Yep, negative 8 kilovars. Remember, it's always a negative number, right? So
I thought the
basically,
negative comes from the equation.
yeah, it does, right? So I'm just saying if this guy is 8, this guy's got to be negative 8, right? So it comes from the fact that if I have a capacitor, right, the S for a capacitor is JQC, like that. This guy's always going to be a negative number, right? I know it's going to be a negative number because the angle, what is the angle always of a, what's the angle
90.
always? Yeah, it's negative 90 if I'm talking about the angle of the impedance on a capacitor, right?
Oh, I see what I was making a stupid mistake. I was doing QL minus a negative 8, and then I was getting 16.
Oh, yeah.
Yeah.
Yeah, I did these in terms of magnitudes up here. Right. The actual QC would be negative 8, but the magnitude of it would be 8. Okay. So what would I do then to figure out the capacitor value? Well, I didn't include the table here, but I basically, if you go back to the notes and the tables I have at the back of the notes, right? It basically says if I have a particular impedance value, you know, I can say V times I conjugate, right? So let's say I have an impedance Z, okay? And I know the voltage across it, and I know the current through it. I can say the power in this guy is V times I conjugate. And I also said, if I wanted to talk about the Q and the P, so let's talk about just the Q values, okay? If I talk about just the Q values, what I could say is that I could relate this as V squared over the imaginary part of the impedance and I squared times the imaginary part of the impedance, right? That was one way to think about the Q there. And I also said that the P was equal to V squared over the real part of the impedance, right? Or the I times the imaginary part, or I squared times the, I squared times the real part of the impedance. All right. And to be careful, these guys are magnitudes. Okay. Like that. All right. So given those, and those formulas are given in the summary tables that I gave you guys there. Given that information, how would I choose the capacitor value?
You want the power factor to be 1, wouldn't you?
I want the power factor to be 1. And I know how much Q I want to provide, right? How much Q do I want to provide? Well, I want to provide 8 kilovars, right?
Yeah.
So how can I use these relationships here to find out what capacitor I need to add.
So it's a V square divided by imaginary of Z. So
Okay,
Z is
these
now Z omega
divided by the
C.
imaginary Z. Why that one? That's right. Why that one, Tom?
Because you know V.
Okay, I know V. Why do I know V? Well, because I put this capacitor in parallel with that load, and that voltage across that load is 250. Okay, so basically what I've got here is I can do a pretty quick calculation now, right? So I can say the Q that I want, all right, I'm gonna put magnitude. The magnitude of that is 8 kilovars, okay, is equal to the magnitude of V squared divided by the imaginary part of the impedance, okay? And so this guy is 250 volts squared. What's the impedance I'm talking about? Well, this impedance is just the capacitor, right? What's the impedance of a capacitor?
1 over J omega C.
1 over j omega c. Okay, 1 over j omega c. So if I talk about the imaginary part of the impedance here, 1 over j omega c. What's the imaginary part of 1 over j omega c?
Negative omega
Negative
C.
90.
Just omega C.
It'd just be negative omega C.
Yeah, be negative 1 over omega c, specifically, right? Because thinking of this as a complex number, it's 0 minus j times 1 over omega c. Its angle is negative 90 degrees. Its imaginary part is the coefficient on the j. Coefficient on the j is negative 1 over omega c. So because I did this in terms of absolute values, right, it's really the absolute value, I guess, of that as well, right? I'm just dealing with the magnitudes here, right? So this is going to become 1 over omega c on the bottom, okay? You guys follow what I did here?
Yeah.
Okay. Now, what I didn't say is what is omega, but that's usually the same value. I'm going to say omega is equal to 2 pi 60, right? What's the frequency F?
60.
Yeah, 60. So 60 hertz is, in the US at least, that's normal. The only other thing you really see in the world is F equal to 50 hertz, which happens in a lot of the rest of the non-North American grid. All right.
Is there any reason for the difference?
Some history to that. I don't know. I don't know why the Europeans did it differently. Yeah. I don't know. 50 hertz goes better when you're driving on the other side of the road or something. I don't know. Not sure what the reason is. I know why they did 60 hertz. It drives clocks. It sets the timing on clocks quite nicely, but that's a different story. So if I want to figure out the size of the capacitor, it's pretty straightforward now. Basically, I have magnitude of QC equals 250 squared times omega, which is 2 pi 60 times C, right? How did I do that? Well, if I have a 1 over omega C, it just becomes that. Okay, so if this is equal to 8,000 vars, I got to be careful here about all my units. Comes 8,000 vars like that, the C value becomes 0.9 microfarads. All right, so it's pretty big. No, it's not that big of a capacitor, right? But if you do that math, that's the capacitor value that you work out to. Let me make sure that doesn't seem quite big enough. Let me do the math on that real quick. So 8,000 divided by 250 squared times 2 times pi times 60. Yeah, that's a bigger capacitor. Yeah, okay, that value didn't quite seem right to me. Okay, so 250. So if I do the math, right? So the 8,000 divided by 250 squared times 2 pi 60 times C, so the C value works out to be 3.395 times 10 to the minus fourth farads. All right, is the size of the capacitor that I get from that. All right. So, so oftentimes if I look at that, this guy, this tells me I've got 339.5 microfarads is the value of the capacitor I would have for that. Okay. All right. So, and I could find that capacitor, right? You'd have to find a capacitor that has that size. The important thing is if you really had to do this problem, you have to find a capacitor that was rated for that voltage, right? That can handle 250 volts. All right. Which you could find that. Okay. So if I did that, the question now becomes, all right, so in this particular case, the SL is now this. All right. It's now just the 10 kilowatts. The load's still getting the 10 kilowatts that it did before. All right. Now what I want to do though is I want to say, well, how much did that change the current? So let's say I want to figure out what the magnitude of I sub S is. How do I figure out the magnitude of I sub S now?
Magnitude of SL over V.
Yeah, so if I look at this guy here, this guy is SL is equal to the voltage across that load, right, times I sub S conjugate, all right? And the voltage across that load is 250 with an angle of 0 degrees, right, times IS magnitude with whatever angle that guy has, right? So if I look at this, and it's negative angle because it's a conjugate, right? So what I would say is magnitude of SL divided by the magnitude of the voltage, right? Magnitude of the voltage is equal to the magnitude of the current. In this case, what's the magnitude now of that, of S in this particular case?
Just 10K.
Yep, 10,000. Voltage hasn't changed, it's 250, right? If I do the math on that, that works out to be 40 amps, okay? So what that means is I sub S went from, it was 51.225, and it's gone down to 40, okay? It's gone down to 40 amps. So I've reduced 11 amps, all right, from that guy. That's pretty significant. All right, the fact that I've reduced it that much is pretty significant, right? So in this particular case, what that says, the losses in this resistor, right? I calculated here, I squared R. The differences here, this guy is 131.2 watts. This guy is 80 watts. So I've reduced about 51 watts of loss in that line, okay? So in this case, the important thing is, right, there's less power loss. The key thing is the customer needs 10 kilowatts of energy, all right, to be able to do whatever it is the customer is doing. All right, so this customer apparently needs 10 kilowatts. Just to give you a sense, that's roughly the same as about 2 houses, all right? So about one house is about 5 kilowatts peak, all right? So that says that there's about 2 houses worth of stuff going on in terms of useful work at that particular case. That means less fuel from the utility, all right, is required. Now here's the thing, so 50 watts doesn't sound like a huge difference, right? But if I wanted to talk about how much energy that is, let's say this guy required 10 kilowatts 24/7. How would I figure out the amount of energy that 50 watts means? So if I know so how does energy relate to power?
Power is the amount of energy consumed in a given time period.
Not quite. How does energy relate to power? What is power by definition? Not V times I.
D work.
Rate of change of energy, rate of change of work, you could say it that way, right? It's a rate of change of energy, right? So we said power is equal to, we said the partial derivative of work, right? Partial derivative of energy, right? So if I wanted to figure out how much energy this 50 watts was going into, how could I figure out energy from power?
Time to the time.
Do what?
multiply to the time.
Well, I mean, technically, right? If
Derivative.
power is the derivative of energy, that says integral, right? Right. So that which if it's a constant power, that works out to be a very simple thing, right? So let's say I had 51 watts. So 51 watts. And I was doing it 24/7, 365 days a year, right? So I'll multiply by 24 times 365, like that. All right. This is hours here, and this is watts. Okay, so that works out to be, if I do that math right there, let's see, that will become 51 times 24 times 365. So that becomes 446,760 watt hours. Okay. Now, somebody who's ever paid an electric bill, how does the utility bill you for, how does the utility kilowatt hours? All right, kilowatt hours.
So you're saving like some money.
Yeah, so if you look at this, so 446,760 watt hours, that would work out to be what, 446 kilowatt hours? All right. So that's how much less energy the utility would need to use, all right, to supply you your 10 kilowatts. All right, there is losses that they have to incur, right? So what they're saying is if you reduced, if you increased your power factor and reduced your need for reactive power, they would need to supply that much less kilowatt hours, which would basically mean less fuel cost to them. All right. So this is a common type of problem to solve in power, is to say, okay, I want to modify the power factor, all right, to something different. Questions about that process? All right. So, just as an example, right, this is, the utility gives you an incentive to do this kind of thing. So this is an example. So I pulled this from Duke Energy's Carolinas, right? So this is their rate structure for a large customer. They don't worry about the power factor of your house, okay? That's pretty negligible to them. But if I'm talking about like the airport, let's say, or some factory or something like that, some big customer, right? What it says here is if your average power factor is less than 85%, they will basically, they'll change. So what this says is if your power factor is 0.8, so if it's somehow less than 85%, 0.85, they will basically come up with a multiplier to charge you more than what you actually used, because of the fact that you did not do what you could have done to help them. So what they're doing is they're trying to increase, if your power factor is low, they're trying to increase your bill to try to incentivize you to do something to reduce your Q. They're making you pay for their losses, right? And that's allowable. In other words, they don't do this to you, to Joe customer, right, at a residential level, but they will do this to a large customer, all right? It is 100% legal, because every rate they choose is voted on by the utility commission.
The Robin Hood of electricity.
Yeah, so the utility commission approved this, and this has been around for 100 years, that if you're not doing something on your side and that's causing an impact to the system. In other words, here's the thing. So you pay Duke for their fuel. You're basically reimbursing them for their fuel costs. All of us are when we pay. So what this is saying is, if you're an industrial customer and you're not doing everything you can to reduce your fuel costs as a residential customer, the utility commission is saying it's fair to give this large customer an incentive. Yeah, it's an incentive is what it is. They're being given an incentive to reduce their Q in order to hopefully pull down the bill for all the ratepayers. If you look at, this gets into, we're way beyond what we need to worry about for this class. But the utility commission, Duke goes to the utility commission and says, this is how much it's going to cost us to give power to everybody in our territory. And the rate gets set based on that. So if somebody is using more than they need, it's well within Duke's rights to charge them more so that it charges everybody else less.
By that, if they could get the commission, let them do that to residential.
They-
houses.
they-
So every month they can send out a dude with a new capacitor.
Yeah. Your queue is so negligible that it doesn't matter. Like I said, I'm talking about a customer who's on this large generation service. Just to give you a sense, your peak load, I said, Duke assumes everybody's house is about 5 kilowatts. Peak load. That's peak load. That's not all the time. That's peak load. So that's probably on a hot summer day when the air conditioner's going. All right. By comparison, the buildings that I could tell you on campus, the peak load that I know of, Fretwell, is about 1 megawatt. Okay. So you're talking about a factory, a factory would be,
The Tesla super factory.
well, yeah, you think about something like that, it'd be pretty big. So it's a very different story, your house versus, there's 200 of your house is 1 Fretwell. Right.
So how would they change the power factor to, increase the amount? What would they do to?
So they would just charge you more. They basically come up with this factor that allows them to charge you more.
I guess I'm asking, how do they affect the Q? Is Q the capacitor?
So we put this capacitor in parallel to lower the Q.
Yeah.
And if what they do is they just use the meter and they measure your power factor. And if your power factor is too low, then they say, we're going to charge you more. And trust me, if you're a customer that is impacted by this kind of thing, you have an account manager and there's all sorts of stuff. I mean, they know what they can do to, yeah. It's not like you send a bill to grandma and grandma pays it. This is pretty serious stuff at this point.
How would we
Yeah.
apply the capacitor or anything as far as
You just got to put it in parallel with the load. So somehow you got to find where the lines are coming in, and you got to. You guys want to know real stuff all the time. Yeah, I put capacitors in parallel essentially with where the power is coming in. Yeah, we could do fun times about all kinds of real world problems. Probably it'd be a lot more fun. All right, good questions. So in terms of the process, basically what I got to do if I'm doing this, right, I got to find the complex power of all the loads, right? So if I have multiple loads in parallel or something like that, I got to add those up like we did last week. I got to determine how much Q is needed. And I shouldn't, it's just to make S equal to P, but it's not necessarily just to make S equal to P. And I'm going to look at a quick example of this, but I need to determine how much Q is needed to hit the target power factor. All right. So if the load has positive Q, then I need to add negative Q. So I need to add a capacitor in parallel, right? If the load has negative Q, I need to add positive Q, which means I need to add an inductor in parallel. All right. Now, like I said, most loads don't have negative Q. Most loads have positive Q. All right. And then basically, I use that reactive power relationship to figure out the correct L or Q value, right? Which is basically this guy, right? That's our overall steps in the process. All right. So it's pretty straightforward, but if you look at the problem, I don't know if it's 2 or 3 in the homework. All right. Problem 2 or 3, what I say is the load starts out with a power factor equal to 0.707. Okay. And I tell you to get it to be 0.95. So I don't tell you to get it to unity. All right. And that's often typically the case. You try to get it to something like 0.95. So if that's the case, what would I do in that case? So if I have 0.707, I don't know what that's going to be, but it's something like this. My S is here. My P is here. My Q is here. Okay. So Q load, S load, P load. If I wanted to get to 0.95, what does that mean? If I want to get to 0.95, where would my new S vector be?
Lower.
Lower, not, so if I got to unity, where would it be? Well, my S vector and my P vector would be the same. Okay. If I was getting to 0.95, that means I would get it to maybe somewhere like this. All right. This would be my SL new. Okay. So how much Q do I have to supply in that case?
That's a lot less.
Yeah, so basically the amount I would need to supply is the difference between here and here. Right? So I don't need to supply the total QL, just a portion of the QL. Okay. So let's just say, so Q, let's say QL for sake of argument is 1 kVAR. 1 kVAR. All right. And let's say at 0.95, that Q is equal to 100 VARs. Then how much QC does the capacitor need to give us? Yeah, so negative 900 VARs, right? Negative 900 VARs, or the magnitude of QC is 900 VARs. Like that. Okay. Does that make sense? Okay. So what I ask you in the homework is I think I ask you for a Q target. So this value right here would be my Q target, right? Which is the value that it would have at 0.95. Right, so that's my target value. All right, I think I ask you, what is QL? What is the Q target value that I want to achieve? How much capacitor Q do I need to make that happen? And then what size capacitor do I need to make that happen? Okay. All right. And then I ask you to do a calculation on the energy like I did there. Okay. Questions there? There will be plenty once you start doing the work, I'm sure. No questions online?
Is there a reason we don't shoot for unity?
It's usually almost impossible to ever truly hit unity.
That would require ideal elements.
Yeah, I mean, well, it's not that it requires ideal elements. It's just a value that, you know, we don't know what your P is going to be. We usually know what your maximum P is going to be, but your P is always kind of changing around a little bit. So usually they just shoot for 0.95 or 0.9 or something like that. Like in this particular case, here's the thing. Duke's, like in this case, Duke says be better than 85%. So chances are you would shoot for 86%, right? You know, just to, because it's going to cost you more money to go all the way up. So you give yourself a little bit of safety factor, right? To make sure that you're always.
Is there a reason why you theoretically go higher?
You could go higher, but it's, I mean, these capacitors are non-trivial cost, right? So you know. So you would do a number based on those calculations. Okay.
Does a capacitor normally cost online?
You guys are asking me, he's asking how much capacitor it costs. It all depends what the capacitor is doing and all that. In this case, 250 volt capacitor, that big is probably expensive, yeah. Plus there's racking and all kinds of stuff to install it. Right, this capacitor, you know, this isn't like, there's not like a breadboard where you drop this guy in there, right? This guy's going to be in some switch gear and stuff like that. Yeah. Yeah. No, this is not like your lab kit capacitor. Yeah. All right.
This is one where we need to do some images from.
Well, no, you don't need that. But all right. You guys will have questions, I'm sure, as you get into doing that. It's pretty straightforward. It basically is you figure out what the load is, and then from the load, you figure out what your target is, and then how much capacitance you need to supply that. Okay. All right. Which brings us into starting our last topic, which is to say, what about a three-phase power system? All right. So what we've learned up till now is single phase power, which single phase power, basically all that means is we had one voltage source, right? One voltage source that supplies. That's what you have at your house, all right? But in reality, Duke, if you go to a generator, a Duke supplies, any generator supplies three phases. So if you look at a generator, what comes out of a generator is three voltages, okay? The three voltages that come out of it, you know, the exact amplitude of them depends on how big the generator is. But you get three things that are 120 degrees out of phase with each other. All right. So what I have up here on the screen is if I had 120 volts RMS essentially what you get is that the voltages that come out of a generator, just because of the way that it's wound, right? This was Tesla's big invention when he determined this, is if I put those windings 120 degrees apart from each other spatially inside of a generator, then I'll get voltages that come out of that generator that are 120 degrees apart in time. All right, now we'll talk in a minute here about why that's done, okay? But essentially what I get is 3 voltages that are 120 degrees out of phase with each other. So here's what that looks like, right? So here's VAN, VBN, and VCN. What you see is that their peaks happen 120 degrees apart from each other, okay? So if I were to draw the phasor diagram here, right? VAN, and there's some terms here. So notice if what I'm showing is the outputs of a generator. All right, and so there's 3 power lines that come out of a generator. And then there's this guy down here called N, the neutral. All right, so A, B, and C. Those are the phases of the output. And then N down here is what we call, what does N stand for? Anybody know? It's neutral. Okay. It's basically the return wire. Right? In other words, it's where, if I had current leaving phase A, that current would come back on N, right? Is the way that works. Okay. All right. So if I draw this out here, if I draw the phasor diagram, VAN, which is the voltage from A to N, all right, that's what that means. All right. And you can do a KVL around the loop that includes N, this source, and this guy right here to say VAN has to be 120 angle 0. Where would I draw VBN? So here's VBN. Where would I draw that? Somebody
This is
online.
3.
Quadrant 3. So it'll be over here. VBN. And then VCN would be up here. So there's 120 degrees here, 120 degrees here, and 120 degrees here. All right, so I got 120 degrees between all 3 of those things. All right, now, maybe I'll jump ahead a little bit here. So why 3-phase? There's 2 main reasons why we use 3-phase. So first of all, first question is why not? Why do we do this? Right? Why generate 3 voltages that are 120 degrees out of phase with each other? If I had a single phase setup, all right, so here was a load here. Here's VS and ZL, right? What was the complex power here? Well, so we determined the complex power, but we also determined initially is we determined what we called P of T, what the power looks like as a function of time, right? What does the power look like as a function of time in this setup?
Sinusoidal.
What's that?
Are you asking if it's the sine wave?
Yeah, so it's sinusoidal, right? So what we said was, if I had a purely resistive load, this is what I would get, right? This would be for a pure R. And if I had a pure reactive load, this guy would become like this, right? Where it was half the time above 0, half the time below 0. Now, we don't think about that P of T very often. But what we said is the power has 2 components, right? It has an average component, and then it has this sort of pulsing component. If I do a 3-phase load, the power of a 3-phase load is power on phase A plus power on phase B plus the power on phase C. That becomes simply 3 times the average power on any one of the phases. And it does not have that pulsing component. In other words, it doesn't have that 120 hertz. Now, to derive that, I gotta basically go in and I gotta talk about, well, the fact that VAN is 120 times the square root of 2 times cosine omega t, and VBN is 120 square root of 2 times cosine of omega t minus 120. So in other words, if I calculated VAN and multiplied it by IA, and took VBN and multiplied it by IB, and took VCN and multiplied it by IC and summed that up, what I would get is a constant value instead of a pulsing thing like this. All right, so one of the reasons why we do it is basically it gets rid of this pulsation, which is really important if you're talking about being able to use a large motor or something like that. I don't have to worry about these sort of pulsations in power. That makes, I still have P and Q and all that sort of stuff, right? But I don't have this pulsation, which is really good from the perspective of a large motor or something like that. All right, and so this was sort of a big discovery of Tesla long ago, right? Was that this was a better way to drive a machine than having this pulsing situation. So he developed three-phase machines. Now there's one other reason, which we'll see here in a minute. Okay. Now we're not going to get too heavy into three-phase, but one of the important things about this is people talk about two things. So right here I gave you VAN, VBN, and VCN. Those things, VAN, VBN, let me do it this way, VBN and VCN. People have different names for them. I call these line to neutral voltages. Line to neutral voltage. All right, sometimes people will call that phase voltage. I don't want to get lost in sort of names and definitions, but sometimes people do call those phase voltages. Oftentimes people don't talk about the line to neutral voltage. What they do is they say, well, what happens if I measured the voltage, let's say right here, VAB?
Are these phase voltages independent of each other, or do they make up like one?
So VAN, VBN, and VCN, they all have the same amplitude. So if you look at the picture here, they all have the same amplitude. They're shifted by 120 degrees from each other. All right. So they should always have the same amplitude because they're coming from a machine that's just spinning around and basically producing three sine waves at its output.
I guess my question is, these voltages are...
I can think of them as independent sources.
Okay.
Yeah, I think that's what you're asking, right? Yeah. I can think of them as three independent sources. All right. So VAN, VBN, and VCN are the line to neutral voltages. But people often talk in terms of VAB, VBC, and VCA, which, what do you think I call those?
Line to line.
Line to line. Line to line voltage. Now again, sometimes people will call that line voltage. All right. I won't get, I try to be very clear when I ask this, line to neutral, line to line. All right. Because I don't want to get lost in definitions on this stuff. VAB, VBC, VCA. All right. So how would I figure out VAB? So VAB is the voltage between A and B, those points. Right. So what's that have to be? If I do a KVL, what does VAB have to be? Just looking at this picture here.
It's VAN minus VBN.
Yeah, VAN minus VBN. All right, it's just those two things subtracted. So, if I did the math on that, all right, what I would get is this result here. So here's the drawing I have. So VAN, VBN. This guy here is VAN minus VBN. What I see from this is if I have VAN, VBN, and VCN equal to, let's call this, they have a magnitude V. We'll say this guy is 0 degrees, negative 120 degrees, and negative 240 degrees. All right, first of all, you guys follow what I did? So VAN is at 0. VBN is at negative 120. This guy is at negative 240. All right, so where are my measures? This is the negative 120. This is the negative 240. Okay. If those are my voltages, what I find is that VAB, VBC, and VCA. What I find is that there's a 30-degree shift between the line-to-line voltages and the line-to-neutral voltages, and they become a factor of the square root of 3 bigger. All right, so square root of 3 times V, square root of 3 times V, square root of 3 times V. And this guy has an angle of 30 degrees. This guy has an angle of negative 90 degrees. And this guy has an angle of 150 degrees. All right. So essentially, one of the questions, if you look, you get to the last, I think, 2 problems in the homework, right? I basically give you, I think in each of those cases, I give you one of the line to line or one of the line to neutral voltages, and I ask you to find the phasors for all the other ones. So that's what I have right here. So you guys may have heard of numbers like this before. Like, what's the RMS value of the voltage we have at a wall socket?
0.77.
So what's the RMS value of the voltage at a single wall socket? Like if I just measured here, what would the voltage?
120.
120.
Right?
That's an RMS.
That's RMS, right? Again, they always say RMS. What that says is, if I look at the line-to-line voltage, it would be 120 times the square root of 3. So in this building, for instance, in Epic, right? If you go to one of the outlets might be 120 degrees out of phase with each other if I measured the voltage between any 2 outlets. Okay. So basically 1/3 of the outlets are on phase A, 1/3 of them are on phase B, 1/3 of them are on phase C. So if I did the line-to-line voltage, I would get square root of 3 times that, which is 208 volts RMS. So if you've ever heard the term 120/208, that's where that comes from, right? You have a 120 line to neutral voltage, 208 line to line. Now you may also have heard of a 480 volt system. All right, that's a line to line voltage. Anybody know what the line to neutral voltage is that goes with that? Divided by the square root of 3. See if anybody's
277.
277. All right. All right. Those are pretty common values that you get. All right, in a building, for instance, right? 480. 480 is pretty normal. Like coming into this building, any large building, you're going to usually get 480 volts RMS. All right, but line to line, and then there'll be 277 line to neutral. Okay. All right. So when I get into these situations, we're not going to talk a lot about this. I'm not going to bog you down in the details of this, but we talk about 2 types of loads. And you learned probably in Network Theory 1, they talk about the Y to delta and delta to Y transformations, and there are these ugly equations. I'm not going to deal with the delta to Y stuff, but there's two ways of thinking about your loads and your sources. You can either think of them as delta connected or Y connected. Okay, so what that physically means, the top here is Y, and the bottom here is delta. Okay, so what this says basically, the way I think about this is like this. If you looked at this building right here that we're in Epic, you basically would try to get 1/3 of your loads on phase A, 1/3 of your loads on phase B, and 1/3 of your loads on phase C. So that way the impedance on each load is approximately this, or impedance on each phase is approximately the same. All right, so usually you try to set that up. We're not going to deal with going between delta and Y. All right, what we're going to deal with in this class is we're going to deal with this picture right here. So you have, I think, problem 5 on the homework deals with this picture right here. Okay, problem 5 is going to deal with this picture. So it's pretty straightforward to deal with the circuits that we're going to deal with. All right, they're not going to be too bad. We're going to jump in on Wednesday to talking about power in 3-phase systems, which to do that, I don't even need to really think about the circuits too much. All right, we're going to think more about the power going on. All right, so if I have, let's say I take that same picture that I had right there. Okay, here's VAN, here's VBN, and here's VCN. Okay, And let's say I hook up a load that is, let's say 1 ohm. Let me do a bigger value. I'll say 10 ohms and J 10 ohms. All right, again, that's a typical way of writing this is I just gonna call that impedance. It's like that. And it's gonna be the same impedance on all 3 of the lines, okay? The thing I wanna talk about here real quick before we wrap up is how would I calculate the currents in any of these cases? Yeah, it's pretty straightforward to calculate my currents. All right, it's pretty straightforward to calculate my currents. So here's IA, here's IB, here's IC. How would I calculate, let's say, IA? How would I
B plus ID.
do what?
Ohm's law.
Yeah, so what loop would I be going around to do this, first of all?
With the neutral.
Yeah, so I go around a loop that included this outer mesh here, right? I'd go around that outer mesh right there. So I basically would redraw the circuit and say I have VAN here. And then I have 10 ohms and J 10 ohms, like that. And I have, that's my current I sub A, okay? It's very simple to do it, right? So how would I calculate I sub A? Well, I sub A would just simply be VAN divided by the impedance of that line, which is 10 plus J10. Very simple to do it, okay? How would I get IB and IC?
Same concept.
Same concept. Now, if I look at that, what's going to happen? Well, if I did IB is going to be VBN divided by 10 plus J10, like that, right? What's going to be the difference here?
Your phases.
Basically, if I look at this guy is going to have some angle. IA is going to have some angle. So let's just call it this way. It's magnitude of IA, and then it would have an angle. Let's call it phi I, like that. This guy is going to have the same magnitude, isn't he? What's going to be his angle?
Wouldn't it be the angle plus?
Minus 120.
Oh, minus.
Minus 120, yeah. And then if I looked at phase C would be the same thing. All right, be the same magnitude. So in other words, I don't need to do the B and C circuit, right? For the B and C circuit, they're going to have the same current, but their angles are going to each be shifted 120 degrees apart from each other. So in phase B, it's whatever angle I have on A minus 120. On C, it's whatever angle I have on A minus 240. Okay, it's pretty straightforward to do it. Now, what does that mean for this guy right here, I sub N? He's got IA, IB, and IC all returning back to the sources through that wire. If I look at this, if I get this situation, right? So right here I have IA, here I have IB, here I have IC. At that node, I can do a KCL and say IN is equal to IA plus IB plus IC. I add those up. If I get this 120 degrees apart thing going on, and the currents are all the same magnitude, that guy's equal to 0. All right. That's the other reason why we do 3-phase. Because what it says is, if I built this circuit here on the right, I would need to have a wire supplying the load, and I would need to have a wire returning the current. But what this says is, if I build a balanced 3-phase system like I have right here, and I sum the currents up, there's going to be very little current on that neutral wire, almost 0. So it says I need basically half the amount of wire to be able to supply one load, right? So that makes for a much more economical system in a lot of cases. All right, so there's 2 reasons why we do 3-phase power. This is one of them. This is probably the main reason, right? It leads to a much cheaper investment in the wires that go out there. And copper is pretty expensive. You may have heard people going around with sawzalls trying to cut copper out of places, right? You can make good money doing that, right? Copper is expensive, and this is why it's done. Okay. All right. So the problem that you have in the homework is very similar to this. The last problem on the homework we'll talk a little bit more about on Wednesday, which is how I deal with power in three-phase. But this is plenty to get you started with how to approach the problem, the homework, problem 5. All right.